Awesome. Thanks, Will. Thank you for the invite. It's actually quite excited to be here. I'm going to share some of our recent landslide research that we're doing at the Alaska Earthquake Center. Our work on landslides really took off after the discovery of the Barry Arm landslide in 2020. It's located in Prince William Sound region in southern coastal Alaska here. And most of you are probably familiar with this landslide, this story of how it was discovered and the particular landslide, or maybe even visited the site during the SSA conference last year in Anchorage, where this photo was taken. Since then, we've actually made a lot of progress. We developed a detection system that's currently running in real time. We're still testing this. And you're actually seeing the system in action here in this time lapse. So my goal today is to walk you through how the system works, starting with why we should be monitoring landslides, and mention some of the challenges we have in landslide detection in Alaska we are facing. Also give you some information about what actually seismic monitoring can provide in real time for these kinds of hazards. And for the remainder of my talk, I'll give you some insights into recent landslide detections, including a surprise event at the end. So the Barry Arm landslide is a classic example of this kind of landslide hazard we're seeing in the Prince William Sound region. So the Barry Glacier here has been retreating for early 1900s. So as a result, this slope, Barry Arm, has been slowly moving because it's actually losing its support. It's been failing. So it's actually a huge slope, a huge mass we are facing with. It's 500 million cubic meters, the estimates of this volume. And it sits right on top of the water. So if this were to fail completely, it has the potential to create a tsunami with larger than 2-meter peak wave heights near Whittier, the closest town, the populated region, which we are actually currently worried about. And of course, cruise ships are active in this region and also adjacent fjords that we are also worried about. Since the discovery of this landslide, the Barry Arm landslide is here now, and the Barry Glacier is here. This landslide has been monitored quite heavily. There are a variety of instruments here, a ground-based radar, an infrasound array. At Alaska Earthquake Center, we put 2 broadband stations. One is Barry Arm Top, that's sitting on top of the landslide, and then one across the fjord, BAE, Barry Arm East. And there's also tide gauges across the fjord that would see the incoming wave if there's a tsunami in this region. So the challenge is that these tide gauges could detect an incoming tsunami within 5 minutes after the landslide initiation. And what we want to provide is that we want to see if the seismic monitoring can provide a meaningful detection in less than 5 minutes, basically. So most of you already know that we don't regularly monitor landslides like earthquakes. It turns out that the nature of landslides are quite different than nature of the landslide mechanics are quite different than earthquakes. Landslides start slowly. They don't have P and S waves to pick. So simply routine monitoring earthquake techniques don't really work for landslides. That's why there are currently no monitoring systems in the United States to issue a real-time warning for these kinds of hazards. And of course, we're in a unique place like Alaska, right? So this adds more challenges to this effort. So here we are looking at day of seismicity recorded at Barry Arm Top Station. It's sitting on top of Barry Arm. And each row is showing a half an hour of seismicity. And since Alaska is famous for its earthquakes and high seismicity, there's always a lot to look at in these day records. And quickly you can see there's an magnitude 4.4 coming from Cook Inlet. And then if you were to look closely, you would even see more. So
this ANSS thing is on Teams or something?
Here's a few I could. Here are the few of the seismicity that I could pick different than earthquakes. There are like glaciers in these records, glacier signals, smaller rock falls, avalanches. And since this Barry Arm landslide is covered with 3 glaciers nearby, this is actually making our job a little bit more difficult than what it should usually be. And there's actually a hidden landslide signal in this record that I will reveal later in this talk. So as I said, we are asking the question of like, can seismic actually provide a meaningful detection in less than 4 minutes? So what do I really mean by this meaningful detection? So we want to see if we can provide a location estimate quickly that would say us, okay, there's a landslide happening near the coast or no. And also we want to provide a volume estimate that would, again, quickly say if the incoming mass is enough to create a tsunami or not. And also we want this to happen quite quickly, hopefully within 4 minutes or less than that. And this is intended for real time, so it should be robust for real-time monitoring challenges like station outages, prop data, false alarms, things like that. And of course, Barry Arm is not the only landslide with this kind of hazard. So this map is taken from a recently published USGS report where they mapped landslides with similar risk in Prince William Sound. So you can, all of these names actually had landslides we are concerned about. So they mapped 43 slowly moving landslides, and 4 are actually comparable to the Barry Arm volume, and 11 of these are potentially tsunamigenic. And with the climate change, these glacier retreats happening and also extreme weather events, this hazard is becoming a serious threat, and we want to be developing these capabilities across a much wider region. So now that why we know why we should be monitoring landslides, before diving in how we are actually doing it, I want to give you a sense of just how massive these events can be. And coming from an earthquake background, I find it a little bit hard to wrap my head around, like what does actually landslide volume mean? Like, 5 million, 500 million cubic meters. These all sound huge, right? At least to me. So for comparison, an Olympic-sized pool can hold 2,500 cubic meters of water. So if we were to scale it up a little bit to put into perspective, let's look at some few historical landslides in the United States. For example, the Oso landslides that happened in Washington was about 8 million cubic meters, which is an equivalent of 3,000 pools almost. And then the Town Fjord landslide that happened in Alaska is 10 times larger than that, with 76 million cubic meters, which is equal to 30,000 pools or so. So that puts actually the expected Barry Arm landslide at the extreme end of the spectrum, with 500 million cubic meters of expected failure, which is roughly equal to 200,000 pools. So to develop a detection approach, we studied historical landslides in southern coastal Alaska, 9 landslides, very well studied events. So you can see the distribution here. We actually chose these at different settings intentionally. We wanted to see how these signals look like in different settings and also with different station distributions. And these are all very well studied events. They all have known volumes and locations from like extensive field work and also from imagery as well, and from seismic. So here's one of the landslides we looked at. This happened near Barry Arm. Here's the location. And the inverted triangles are showing the stations that recorded this event. So landslides radiate energy at 2 scales. So on the left, we are looking at a long period move out, which mostly represents the bulk acceleration and deceleration of this moving mass. And right panel, right record section shows the short period move out. This mostly represents the smaller interactions within the landslide body and with the surface it is moving on. And we are looking actually at stations, increasing distance from the source of very arm stations at closer, and then going to a distance about 220 kilometers, about 2 degrees. So if you were to look at only longer periods, what we are seeing is that these signals are quite simple and distinctive. You can actually visually see it really easily. They do attenuate very slowly as well. Whereas if you were to look at the high frequency move out, these are quite complex and they do attenuate actually quite quickly. We are not seeing this one, for example, after a degree or so. And another caveat with these signals is that they are very similar to nearby glacier signals that we want to avoid. So that's why we decided to actually work with the longer period signals and based our approach on these signals. So what we are doing is we use back projection to trace the signal back to its source. So what we are doing is we shift the traces back in time using a single velocity, and at the landslide location, these signals actually look perfectly. They actually align perfectly in time, as you can see here after the time shift, and they are quite similar. So this similarity of these waveforms actually open up a large set of techniques that we can use already established in seismology to establish the degree of similarity. Yeah. So we are using, for that regard, we are using amplitude stacking to measure the degree of similarity in this case. So if we were to turn the question around for an unknown landslide location in this particular region, what we can do is we can do a grid search, basically. And at each grid point in this region, we can look for this best alignment of traces. So this is what that color map is showing here, the degree of similarity. And red in this case indicates higher similarity, which is likely a landslide signal. So we did this for all of the landslides and got generally good estimates. Here's all of the results we had for amplitude stacking. For very arm events, for example, we are getting really good results, and also for the Red Glacier event. At some cases, for like Mount Le Perouse, we have a large location error, but as I said, we wanted to test edge cases. So station distributions are sometimes not ideal, but what we are generally seeing is that these are showing robustness to bad data and also fewer data as well. And it's actually giving us good estimates, rapid location estimates within 4 minutes. We also developed an approach to relate seismic amplitude to volume. So this plot shows here the relationship we are using for that. What we're doing is we're plotting each landslide with their known volume from the literature. And the x-axis is showing the distance corrected amplitude for each event, the maximum amplitude of these long period signals. So this is the black line is the fit to the data, which we are using the scaling relationship to get to the volume. And this is a first order, very quick estimate to get a rapid answer quickly, enough to say whether the incoming mass is actually big enough to create a tsunami or not. And as this plot shows, we're actually doing a really good job for most of the events. At some cases, we are off by an order of magnitude, which is quite expected. And if you were to actually look at these thinner lines, which is showing the volume error from the literature for these particular events, there's a lot of uncertainty for those volumes as well, which are calculated afterwards, after the landslide happens, usually days or even months later. So now that we have a location estimate and a volume estimate in a quite rapid way, we also want to see if this works in real time, because research is really fun, and we also expect that it's going to work, but you never know. So let's look at how this is working in real time. So I'll show you a time lapse. This will show you the evolution of a landslide detection. On the map here is centered on Berry Arm. So Berry Arm is, oh, my pointer is gone. But so Berry Arm is at the center, and the color map on top is showing the degree of similarity. The right-hand side is the 3-minute waveforms. These are going to change every 30 seconds, and these are actually shifted in time after the back projection. So let's start the time lapse. So this is changing every 30 seconds. We are computing this every 30 seconds. The gray circle is showing the location of the degree of similarity, best one. And when this actually exceeds a certain threshold, the system will declare a detection. So we're going to see one very soon. There we go. So we have a detection. It says in red, yes, for detection. The coherency similarity value is about 0.7. There is a volume and a location estimate. And then we'll see it again after the second 30 seconds. We have another detection with much higher coherency and a little bit higher volume. And while the landslide signal is passing by, we are seeing another detection. So these waveforms are actually aligned to see an incoming wave, particularly for Berry Arm. That's why they're not aligning perfectly for the source location. But I'll show you in 2 slides that perfect alignment soon. Okay, I can get back my pointer back. Okay. So we have been testing this approach about 2 years now, and since then we have detected 28 landslides. So here you can see the distribution of these landslides. Every orange circle is a landslide, and these circle sizes are scaled by volume. The ranges of volume we have detected is about 0.1 to 4 million cubic meters. And actually the lower end of this volume is quite interesting, because if you were to look at landslide literature, you would see that long period signals for landslides are actually created for much larger landslides, like a million or larger than that. But here what we're seeing is we're actually detecting really like smaller considered landslide volumes, like 0.1 million cubic meters. The other thing to note here is that some of these events have remote sensing imagery kind of like confirmation afterwards, but not all of them. So this is kind of like a game changer for us as well, because before what we would do is we would hear about the landslide detection, either by someone flying by, or someone finding this in imagery or like something similar. But now we are turning the question around and we are saying, okay, there was a detection in this, there was a landslide in this region. Can you actually go and take a look at it? And this is also quite important because we can now start cataloging these events in a very systematic way and also gather more information. So let's look at that time-lapse event that I showed you. This happened in during summer solstice last year. Here's the detection email we got. So these are these are the kind of like the detection emails we are getting for this approach. It says there's a possible mass movement. We have a time, latitude, longitude, coherency, coefficient, the degree of similarity, and a volume. And it also comes with a map of the landslide location. And you can see now how this is actually aligning in time for this particular source location. Here's before the time shift and then after. And for this particular landslides, we didn't have any remote sensing imagery. So another thing to note is that, so this is our current detection search area with Berry Arm in the center, but you probably have noticed that we have detected events outside of this current search. We do detect landslides outside of this search area, but they are actually located, the locations are off. So what we are doing is we rerun the algorithm after we are seeing that detection, just changing the grid center to that particular location, or just like shifting it a little bit and then locate them. So one of those landslides is the Denali landslide here, which is actually the largest landslide we have detected so far. Let's look closely how this evolved. So this is the email we got for this detection. This is kind of like a previous version of this algorithm, but not the algorithm, but the email. So it kind of like indicates that there is a detection. Yes, this is the location is kind of like at the corner of the grid. And if you were to look at the long period move out, it says that, yeah, there is a signal, but the location is off. Likely this is out of the grid. So when we shift this grid to the northwest, here's what we got: a really nice bullseye pattern for the location. Coherency is actually rather large; it's about 0.9, and you'll see actually why. Here's our landslide signal. This actually is one of the most beautiful landslide signals I have ever seen. I probably don't need to highlight it, but here we go. Here's the move out, and then the alignment in time when we do the back projection. So the location we got for this one is about 1 kilometer away from the ground truth location, and the size of 4 million cubic meters is quite well within the 4 to 6 million cubic meters estimates from remote sensing imagery. So Liam Tony is doing a rather extensive work on this effort. It's about to be finalized and submitted for publication soon. So the park rangers in Denali Park actually use our location we got from this approach, and just went to the site and then got these photos. You can see the landslide up here, and then in a closer photo up here. And this is the hidden landslide signal we looked at earlier at station B80. Here you can see, although this is huge, it could look small in these kind of settings. So I'm gonna now show you a series of landslides that we detected last year, which is I think the most interesting sequence so far that we've looked into. These are the surprise inlet landslides. They're located right here. So on September 20th last year, we detected 3 landslides in a row within a span of an hour. So here's the first landslide. It happened at 11:13 a.m. With a volume of 0.7 million cubic meters. And after almost an hour later, we detected the second one. It's larger volume, 2.3 million cubic meters, coming from the same location. And shortly after, we saw the third one, 7 minutes later, 500,000 cubic meters, the volume is, and again coming from the same location. This is quite interesting because we don't usually see a series of landslides coming from the same region this clearly. So here's a clear look for one of those the maps that we create for detection. This is for the second landslide, the larger landslide. You can see the similarity color map here pointing to this particular location. And here's our signal, move out, and how it actually looks like when it's time shifted in time. So the locations we got from this point to the terminus of the Surprise Glacier. So Surprise Glacier is here. This is our location. And this is actually quite far away from the Berry Arm. So Berry Arm is located about 18 kilometers to the northeast. And the real-time location is actually quite interesting. So because since it's right at the terminus, it means that this could have hit the water. And since we are monitoring this area pretty closely because of Berry Arm, we could actually see if this created a tsunami or not. So shortly after the news about this detection, our colleagues at the USGS found the landslide in the imagery. So we are looking at the Surprise Glacier terminus before and after. So like I think a month in between. So the landslides happened on September 20th. So this after image is taken right after the landslide. And you can see the extent of the source, failed source, with these red arrows. This actually took the parts of the terminus and also indicates, that it actually hit the water. We then had additional confirmation from the tide gauge at Point Grand. So Point Grand is located here, about 15 kilometers away to the east. And then here's a day of record, tide record, measured in this tide gauge. And the wave arrival happening is here, about 10 minutes after the largest landslide. And you can see the frequency content here. So if you were to look closely to this time period, here's the wave arrival. This is the largest wave that was measured was about 4 centimeters. And there is an like hours-long oscillation going on in this fjord after the wave arrival. So this is for us a remarkable event. This is the first event to be detected in real time with seismic, which also triggered a tsunami. So we were able to record these with all of the extensive monitoring going on in this particular region. And these are some photos taken in the field about 20 days after the landslide. You can see the failed source and some of the material still sitting on top of the Surprise Glacier terminus. And here's a closer look to the slope itself. So seismically, this is quite an interesting sequence as well, because it includes a lot of different events. So we're now looking at 1.5 hours of seismic time series in a long period. This is the same frequency we are using for detection. And the stations closer to source are located here, and then it's sort of like increasing distance from the source, which this is about 233 kilometers away. So you can see all of these landslides we detected really clearly. Landslide 1, the second landslide, the largest landslide, and the third landslide right after. So one thing to note here is that the second landslide, the largest landslide, was actually detected by Alaska Earthquake Center's real-time earthquake system with an equivalent magnitude of local magnitude of 2. Here's the notification we got for that one, which is a common thing to happen with large landslides. So one other thing to note is that there's also a teleseismic earthquake passing by between these events. You probably already noticed it. So this is an event coming from Tonga, magnitude 5. It can be clearly seen between the first and the second landslide. So on an algorithmic level, this is actually fascinating because it means that we were able to detect the landslide in spite of this magnitude 5 event while it was passing by. So when we look at higher frequencies in the same time window, we realize there's actually more to the sequence. So again, all three landslides are seen very clearly, as I highlighted here. But if you were to look closely, right before landslide 2, there is a signal, very intriguing. And also there's another signal after L3 here. So if I toggle back, they don't have any long period signals, but these are actually quite clear high frequency signals. So there are a couple of things to note here. So they look very much like the other landslides we have detected. They have both of these have distinct high frequency signals. They have like emergent onsets, and also they decline after peaking the peak to the high frequency. The move out pattern is quite similar as well. Closest at the very arm stations and then moving away, very similar to the other landslides, which means that this is actually originating from the same location. And these are actually trackable at further distances, about more than a degree almost. And there are no low frequency signals associated with these events. So that's why we weren't able to detect these landslides in real time. But we did some further investigation on these by looking at their envelopes and ended up concluding that these were essentially loud but smaller sized events because they didn't create any long period signal. So overall, we have 5 landslides in this sequence. So what triggered these events? So here's a look at the Surprise Glacier terminus. So this image was taken on 2017, and the bottom was in 2024. As you can see, there is almost maybe more than a kilometer of a retreat within these 7 years. And for reference, slope that failed is right around here. So we think that this probably retreat kind of like caused some instability in this region, but the landslide source is actually located quite high above. So we don't really think that this was the primary trigger for these landslides. But if you were to look at the rainfall recorded at the nearby weather stations at Berry Arm, it's actually quite interesting. So I'm showing you the daily rainfall recorded at Berry Arm West and Berry Arm East stations. And this is starting from July to October. And right before the failure, the Berry Arm West, Berry Arm Top station actually recorded quite peak rainfall 2 days before. And we think this probably was the primary trigger, as the rain came in and then created this orogenic storm rainfall, bringing in rainfall to this southern slope. So this is another. So what did we actually learn from this surprise sequence? So this is another photo taken during the SSA conference last year during that field trip. And now on the background, you're looking at the Surprise Glacier terminus, and the red line is indicating the failed slope in the sequence, so surprise inlet events. This photo was taken just 5 months before these landslides. All of us, about 300 scientists, visited the site during the field trip. And we actually had no signs that suggested surprise inlet lines, this slope could actually fail. So this actually probably really nicely sets up the hazard we are facing in this region. So this particular event didn't actually pose a major hazard because it's quite remote, right? So, but it would be very hazardous if it happened in a populated region. And it looks like these events can occur very abruptly, and will happen more frequently with the warming climate. What we've seen actually here is that the seismic monitoring is quite effective at a regional scale with the existing network we have at the with the Alaska Earthquake Center. We've seen that the instrumentation in the Berry arm, the additional instrumentation, could be quite complementary and enhances the detection. But obviously, this is not practical to have it up and set it up for all of the regions that we are worried about. And maybe I've said this already, but we should be. This is a classic example that shows why we should be monitoring these type of hazards and also do the research so that we can actually come up with early warning techniques and prepare for the hazard response. So, which brings me to the final slide that just like shows a sneak peek of what we are currently working on. So as I said, this current detection approach that we are doing is proved to be quite effective, but obviously we want to expand this. So here's our current grid that we are running this algorithm on. Again, Berry arm is on the center. So the scale, this is about 200 kilometers by 200 kilometers large. And I'm showing the new grid that we are working on. This is now by 2,000 kilometers by 1,000 kilometers. Now we are using 44 stations. When we expand this is going to have 200 stations we're going to be working on. We have added some more capabilities like new thresholds to avoid false detections from earthquakes, a slightly improved volume equation, volume scaling relationship. And we are hoping to make this, put this in a test in real time very soon, hopefully in the coming weeks. So stay tuned for more landslide detections from the Alaska Earthquake Center. That's it. Thank you all for listening.